So we've done a lot with lenses and mirrors, so I thought it would be helpful to get sort of a summary of everything we're working with lenses and mirrors, ray diagrams, and the sign conventions for all of those. So to start with, for both lenses and mirrors, we can say 1 over the object distance plus 1 over the image distance equals 1 over the focal length, and that the magnification that you see is equal to minus the image distance over the object distance. It's also the ratio of the heights, right, of the objects that you see, the image height compared to the object height. So this image object can stand for either, where the negative sign means that it's inverted. Okay, so some sign conventions as we go along, and then the rays that we use. In all cases, we can use for mirrors, I'll go ahead and set up mirrors just to sort of set up the convention, and then lenses, right? We have lenses like this, converging and diverging. So these top ones are our positive, so this is focal length is greater than 0. Focal length is greater than 0. These are converging. Okay, converging lenses, converging mirrors. So the rays come together. That doesn't always mean you have a smaller image necessarily. It just means that when they hit the mirror and come back, they're coming together, converging. Same thing when they go through the lens, they're converging. Okay, so focal length greater than 0 means we're on this side. We actually have 2 focal lengths. When we're looking at them, then we can look at our ray diagrams. We have the first one that comes in parallel and then goes through the focal length. So we go parallel and through the focal length. That's a ray, parallel through the focal length. Okay. Same thing happens over here. It's just because these are negative focal lengths, so this is focal length is negative, again, they can still spot at the same place. Then if a ray comes in parallel, these are diverging. It's as if they came from the focal length, okay? So we go like this, and then this is going to come out the other side as if it came from the focal length. Okay, so for the lens, the positive is on the side where light is going to go through. For a mirror, it's on the side where the light is reflecting back. So this is our first ray, the coming in parallel, going out through the focal point. Okay, so now I'm going to show you the second ray. So the second ray will be when we go through the center, go to the center point, and come back at equal angle, or going straight through. Okay, so the second ray is fairly straightforward in all of these cases. Oops, I lost my lens there. It looks basically the same. You have a ray that comes in, hits the center, and comes back out. Ray comes in, hits the center, comes back out. See, it's the same. Here, we've got a ray that comes through the middle and goes back out. A ray that comes through the middle and goes back out. So that's an easy ray to draw, and it's the same in both cases. Okay, finally, the third ray, often the harder one, goes through the focal point because it depends on where your object is, and then comes out parallel. So let's see that one. So that one is going to come through a focal point like this and then go back out parallel, or if your object is above the axis, which is usually the case, you would send your ray like this and then come back out. Okay, same thing, it would look like it's coming from the focal point, so look like it's coming in like this, and then it comes back out parallel. Okay, it comes through this focal point on that side, why I missed that. Like that. And then it's going to come out parallel. Okay? And similarly, it's going to look like it's coming from this focal point. Remember these lenses. So coming from the focal point and then comes out parallel. So putting these rays all together with one image, we have something coming in, going out, coming in parallel, going out, coming in parallel, coming out, going in parallel, going out. That's the first one. We're going to do the center ones like that. Center bounce, center bounce, center going through. And then the last one, like I said, the harder one, this one is coming down and comes out parallel. This one comes down, comes out parallel. And then this one looks like it's coming from the focal point, and then it comes out parallel. Looks like it's coming from the focal point there and leaves parallel. To find out where the image is located, we think about the eye. In the case of a mirror, the eye is going to be obviously on this side. There's our big eye. And in the case of the lenses, the eye is going to be on the right-hand side. So we have the eye sitting out over here, sitting out over here. And so in this case, we're looking for where these rays are all converging, and they're going to kind of converge right about here. For this one, this lens, the rays are all diverging, so they're not going to come together. They're going to come together back here, sort of along that. So right about there. So that's where your image is. Right in there. And then similarly, this one just looks like a mess, right? So if we look where all these rays are coming from the eye's point of view, this red straight one comes from back there. This orange one comes from back here. This green one comes from back here. And there's your image right there. Try to make that highlighted a little bit more. And then for this setup, all of these rays, they're not really coming together at all. We'll pretend like they're coming together right about here, like this. So if we look in the first two cases, the way I've drawn it, these are both real and they're inverted. And we'll see that for real would be a positive image. The image distance would be positive because it's where it's supposed to be located. So a real image means that the image distance is greater than 0. Sorry, that's hidden behind everything. And which means that it's going to be inverted, because I have a positive value here, a positive value here, and a magnification of -1. So I'll make this set up down here. So real image is always inverted if we use one optical element. You could obviously put a second one in to then flip it again. Real is going to be inverted. Virtual is going to be upright, as we can see in the bottom. A virtual image means that the rays aren't really there, look like they're there. So in this case, the eye down here in this bottom convex mirror, notice the straight line, the image is behind the mirror. Well, there are not any light rays back there. So the rays look like they're coming from where they aren't located, look like they're either behind mirror or in front of lens in the second spot. Excuse me. And for virtual image, then the image distance is less than 0. That's negative for virtual. So, in terms of a sign convention then, with mirrors, we have a positive sign when we're on sort of the correct side of the mirror. We'll say the left side of the mirror, if we work from right to left. And we get a negative if we're behind mirror on the right side. For a lens, our sign convention is that we have a positive if we're on the right-hand side, where the light is going through. Goes through, sort of the natural side, if you will, for the lens. And negative if it's back on the left-hand side, or the object side, if you will. And that gives us our sign convention for all of these. We also know that if we have a real, then we have an inverted. If we have virtual, we have upright. The negative lenses and mirrors, so negative lens and mirror are going to give us virtual images. The positive lenses and mirrors can give us either. Positive lens and mirror gives us real when object distance is greater than the focal length, and gives us virtual when the object distance is less than the focal length, which I didn't draw up here, but I did in some of the examples. So this is sort of your summary of where everything fits here, and showing the rays that we use to set up ray diagrams to see where images are located.